Now we're going to look at clustering patient behavior with Python, and in particular, I would refer you to the GitHub folder that is just called clustering, and we're going to look at the clustering patient populations PyNotebook. Okay, so we're going to begin by importing our data. It's in a CSV format, which is very common, and we just read it in with standard pandas functionality. We'll take a look at what it is, and we see what we've got. We've got weight, number of readmissions, number of medications, hours since last meal, blood sugar, blood oxygen, and age. So we've got some data about patients and their readmission statistics at an ER. The first thing I'm going to do, even before I look at clustering, right? Clustering is its own form of exploratory data analysis, but I like to start simpler. So I like to just look at some histograms, right? So what kind of ages are we looking at? And I see we've got people kind of between age 10 and 60. I guess that sort of makes sense. Maybe younger children go to a separate ER. Maybe older people also go to some sort of geriatric specialized ER. So I've got sort of people in the middle range of human ages. And then if we look at the weight, I'm looking at the weight, and it looks like people are around 150 pounds, give or take 50 pounds. And that sounds about right, I guess, for some human populations. So I think, okay, well, I've got a lot of variables. I can't really explore the relationships between all of them, right? Because if I wanted to sort of plot histograms for everything, that would be 3, 4, 5, 6, 7 histograms. And then if I wanted to plot correlation plots, that's 1, 2, 3, 4, 5, 6, 7, choose 2, 7 times 6, 42 plots. That's a lot of plots. So at this point, I think, well, clustering can probably be fairly informative. So what I'm going to do is I'm going to use a Python module called sklearn. This is very actively developed, very widely used. And in particular, I am going to use two things. From clustering, I'm going to bring in the k-means clustering. And from pre-processing, I'm going to bring in normalize. So as with many algorithms, it can be very helpful with clustering to scale your data or normalize your data before you begin your analysis. And the reason for that is, think about how clustering works. We just talked about this. K-means clustering tries to minimize within cluster variance. If we look at the values here, though, for example, age versus weight, the age range is about 50 years in this data set, whereas the weight range is, going from, say, 50 pounds to 250 pounds is about 200, right? So if I'm just thinking of the number divorced from the units, it's 50 versus 200. So just thinking about it, because weight has more intrinsic variation in number because of the units I'm using, weight would end up getting weighed, no pun intended, more heavily, right? So I don't want that. I don't want weight to count more than age just because the units I use to describe weight make the number bigger. That is not what I want. So what we're going to do is we're going to normalize this data, and the normalize function in sklearn will take all of your data, give it a mean of 0. That's less important here. We don't care about the mean, but the other thing it will do is give it a variance of 1. So that means that all of the data will have the same numeric scaling. So weight and age will now both have a variance of 1, which means that one won't be weighed more than another purely because of the original numbers. So we're going to scale our data, and then we are going to just cluster it. And for starters, if I'm only going to cluster once, I'm going to just use a number of clusters of 2. I'm sort of thinking, is there just some very rough binary grouping I can do of the data? I just want to see that. So I generate my k-means cluster here. 2 might not technically be the correct number of clusters in the sense of what the natural number is if we eyeball the data, but in high dimensional data sets, it can be hard to eyeball the data, and it depends sort of what axes you cut along. So as a first pass, just seeing, are there broadly 2 kinds of patients? And then I'm going to run the fit function to then get those labels. So I run this k-means clustering. You can see the nice thing about k-means clustering, it might be fairly rough in some ways, but it's very fast. It's very computationally efficient. I can then look at those labels, and I can see all the labels came back as 0 or 1. And if I want to look at the cluster centers, which is sort of where I have put the center of my different groups, I will have 2 of those cluster centers. They come back as arrays, and I can sort of eyeball them to see if there's a difference. And eyeballing them, for example, I see that this 1, 2, 3, 4, this 5th parameter seems quite different, 0.02 versus 0.0003. Similarly, the 6th parameter seems quite different. So it could be interesting to think about where the variation is coming from, like where we're cutting to create these groups. So I'm going to take these labels and add them as a new column to my data. And then I can, okay, so I take a look at my data frame head, and I look and I see that in addition to things like age and blood oxygen, I now also have a label of 1 or 0. And I can even just think about why that might be. It's better, of course, to look at the metrics, but I'm thinking, well, this is a 53-year-old, 96% blood oxygen, 94 blood sugar, 4 hours since the last meal, 10 medications, and 2 readmissions. And if I think they're the only one with a 0 label versus all these other individuals who are just randomly selected from the top, I think it's really these last 2 columns that have jumped out at me as making this individual quite different from the others. Now, I don't know if that's true, but just randomly eyeballing, and I could try eyeballing more people to get more of a sense. So if I look for more zeros, my other 0 is down here, and that's also a high number of medications and a high readmission rate. So what I can finally do is group all of these people by their labels and then take the mean of every column. And if I do that, actually it becomes very clear that that is the difference, right? That people with a label of 0 have many more medications and many more readmissions than people with the group 1. Now you might say, well, but does that really help me, right? Does that just tells me that problematic people are problematic in the sense of having many hospital readmissions, but their age seems about the same, their blood oxygen seems about the same, the blood sugar seems about the same. Is this very useful? And I would say, well, actually, if you look, one thing that's different is the weight is different. So sure, we can't perfectly predict, but we see that people who tend to have higher medication usage and higher hospital readmissions also have a higher weight. So that's where we find something new, right? Because you could argue that medications and readmissions are very strongly linked, but it's not necessarily the case that weight is. So there we've sort of drawn a new insight, and I would argue that's not an insight I could have drawn from just looking at this original data frame, right, where I have all these possible combos. Clustering has helped me faster get to having some ideas about how hospital readmissions and medications work and how they might be related to body mass. If I wanted to, say, confirm my intuition, I can do things like run a Pearson R, right, to look at correlations between some of these variables in my label. So if I want to see how my labels correlate to my readmissions, I can do that, and I see it's a very strong correlation, right, 0.85 effectively. Another thing I can do is sort of look at the readmissions histogram, right? What's interesting is it's the clustering that has brought the readmissions metric into focus as something I want to think about. If I now look at that histogram, which I didn't earlier, I actually see it does have a funny distribution, right? So as opposed to my weight and my age distribution, which seemed very natural and very Gaussian, sort of what you expect to see in real data, my readmissions histogram, right, has a huge spike just at 1, and then it's sort of spread out, and that already points me to thinking, well, that looks like a combination of distributions rather than just one. And I can similarly, if I look at my labels, if I think about, say, redoing this as not just number of readmissions, but just being readmitted versus not being readmitted, right? So I think if readmissions is greater than 1, I'm going to just call that multi-admission, because I'm theorizing that all of these people are much more like each other than just this one group. And I'm really not just theorizing, I'm seeing that in my clustering. So I'm going to say these people who had more than one admission are much more like each other than they are like these people who had only one admission. So I'm going to define multi-admission as more than one admission, and I'm going to look at how that correlates with my labeling. And I see again that this multi-admission also really strongly correlates. So it's not the number of admissions per se, it's just whether you're a person who is going to be readmitted versus someone who isn't. And so finally, if I just want to get an idea to reinforce my conclusions about how these groups differ, I can histogram my entire data frame according to what label I had put on each individual. And that will take a second, but I can see a few things here that again confirm what I had already concluded. Firstly, that the clustering difference primarily lies in the number of medications and the number of hospital admissions. And then I can also see the weight distributions, right? The weight distribution for those not admitted to the hospital more than once and not on multiple medications tends to be left shifted a bit to lower values. compared to those who are in the group with the high readmission rate. So here what we have seen and done very quickly is gone from a fairly confusing wide data set into strong ideas about different patient populations that we didn't have to sort of impose on the data, but that naturally arose out of the data.